Alright, good morning. Hope everyone's good today. Alright, Wednesday. So PA4 is due Friday morning. Make sure it's accessible to me on Git by 8 a.m. for full credit. Any questions on PA4? Got lots of people coming in, showing me code, working on bugs, which is great. Any issues you want to talk about in class right now? And still kind of seeing a few of a set of recurring issues. One is probably the most common issues I'm seeing are one, not allocating space for the name and plate information in a node, and not using string copy to make a copy of the information you want to store. And so here's the potential setup. Here's your root node, and it's got a license plate, and it's got a first name and a last name, and your main program does some kind of scanf or something to create a first name and a last name. And in your add function, you say node something like this. So your main program reads in, an input line, parses it into some fields, and then says add plate first name, last name. And so in your add function, you take these arguments, and if you say something like node arrow plate equals plate, you find that all of your nodes have the same license plate in them, and every time you try to add a new node, the root node changes magically, right? So what's happening in main is you're saying something like, car plate bracket 50. So plate is a pointer, right? Arrays are always pointers, which means, for example, if we go off to memory here, there's some memory location, let's say it's 50. That's where the characters of your license plate are stored from main, right? It's just a local variable. So you call scanf, and what do? You pass it a 50, right? You say plate, that's the address of it. And scanf, as it reads your input string and parses it using %s as a pattern, it loads it into here. That's why scanf works. Now, if you pass plate to add creates a new node. So here's, a new node. Let's just call it node. So add is called malloc to set up space for a node, so there's somewhere in memory. When you say node arrow plate equals plate, what you're actually doing is you're saying, okay, here's a field called plate in my node. What should I set it equal to? Set it equal to plate. Well, what is plate? Plate is 50. So your node is pointing right here. And even though you created a new node, the plate field is referring to this local variable inside main. And if you call add later on and you create another node and you set its plate area equal to plate, that also points to that variable. And so you build a binary tree, but in each of those trees, the plates refer to this one location in memory. And the names refer to another location in memory where your main program set up space for first name and last name. So if you're finding that all your nodes look the same, or that the root keeps changing, what you need to do is, instead of doing this, do something like node arrow plate equals malloc, and set aside some space. How much space do you need? The number of characters in the license plate, for example, +1. It's a +1 for the null terminator. And so now, instead of pointing up here, this is going to point to some other location in memory, which malloc just gave you. And now you want to read the characters from here and copy them into here. So you want node arrow plate bracket 0 equals plate bracket 0. Node arrow plate bracket 1 equals plate bracket 1, yada yada yada. And there's a function for doing that. It's called string copy. So string copy node arrow plate comma plate. And that copies character for character each byte from here to here up to and including the null terminator, which you made space for. So now this is a copy of the plate that was passed in. From that point forward, if main changes what's stored here, has no effect on this. The only thing that's pointing to this is the node of the tree. Let's see, how to capture ctrl-D. You don't. You look for end of file. So, so when you are reading from standard in, if you hit ctrl-D in the beginning of a line, fgets will come back and report that it hit the end of the file. So if you do a loop like we were doing yesterday, where you just say while fgets is not null, that loop will exit if you hit ctrl-D. You're not actually capturing a ctrl-D. Ctrl-D is ASCII character 4. You never see an ASCII character 4 coming back from fgets, right? What you see is the return value of that function call is null. That's the indication that there was an error or an end of file. And if you redirect standard in from a file, so if you run your program and you say less than some test file, when fgets reads the last thing from that file and then tries to read something beyond that, it'll come back with a null value, and that's how you know that you hit the end of the input. So you could do for your program while standard in is not equal to EOF. Nope, you never see EOF. EOF is meaningless for fgets. And standard in is a file pointer. You don't want to compare it to anything except null. So let's just code this. I don't know where I put it. Alright, I'm going to call fgets to read from standard in into a buffer, and I'm going to take the return value from fgets and print that out. And we're just going to do this two-line program. So if I say HELLO fgets returns something that's not null, and my buffer is equal to hello. If I just hit an empty enter here, just an empty line, then fgets returns something that's not null, and my buffer is, you know, an empty line. But if here, and you can't see me doing this, but you can trust me, I'm holding down Control and pressing D for Control-D, fgets returns null, and my buffer is meaningless. It hasn't been affected. So what you want to do is when you call fgets, check the return value. And if that's null, then you want to go ahead and exit your loop. And %p prints out null as nil, because that's kind of the computer science term we use for null. Alright, let me go back in. My NLR and LRN go backwards. That's a hard thing to do. Well, LRN is not a, yeah. They should be exactly like LNR, except NLR, print your data first, LRN, print your data last. So it's really just where you do the printing of the root node's data relative to your two recursions. Let's see, for the search function, if found, populate first and last and return 1. What does that mean? So your main program, the user can type in a license plate, and the program should show the user the name associated with that plate. That's the basic function of the program, right? Type in a plate and it tells you who's associated with that. So you're writing a search function, and the search function will go through the tree and look for the plate. It returns an integer, 1 or 0, right? 1 says yes, the plate was found, 0 says no, it's not. But the search function also does a second thing. It actually retrieves the first and last name from the tree and returns that to the caller. So when you call search, you're doing two things. You're saying, tell me if this plate is in the tree, and if it is, tell me what the first and last names are. Well, a function can only return one thing, basically, and for this function it's returning an int. So where do you get the first and last name from? Those are arguments that you pass to the search function, and the search function copies the first and last name into where those arguments point. So that's what it means, populate first and last and then return 1. So it's a way to pass back more than one piece of information. And somebody already answered this. It means to copy the first and last name associated with the plate, the first and last, so the main program can print them up. Yeah, what he said. So shouldn't it have to somehow return the first and last? Yes, it returns the first and last by copying them into the arguments. So first and last will be changed in main after you've called search if the thing was found, if the plate was found in the database. If the plate was not found, don't touch first and last. Yeah, you will extend your life considerably by saying nil instead of null, because you'll save a letter. Live 33% longer. So does search actually print stuff then? No, search should not print anything. Search returns the information that main can choose to print. But don't print anything from search. Don't print errors, don't print plates or names or anything like that. Why would they change null? Null is null. Null is a Unix term, C term, right? In C, null is uppercase NULL. In Java, null is lowercase NULL. It's something which is set up in standard IO.H, right? It's a particular symbol that we use. But the general notion of, you know, something that's empty or non-existent should be independent of, you know, whether we use uppercase null or lowercase null or my null or whatever, right? So we usually just use nil. And if we get to red-black trees, we'll use nil for children of leaf nodes. All right, so search returns a string with like %s%s%s. It returns, so the function return is a 0 or a 1. But yeah, if you find the plate, return a 1 and also the names to print. Yep, exactly. Difference between LNR, NLR, and LRN, like only a couple of lines, different code. It's one line. So left node, right. If your tree is null, you're done. Otherwise, traverse the left, print the root node data, and traverse the right. So that's your in order traversal. If the tree is null, we don't do anything. Otherwise, traverse using the same function, the left subtree, print the root data just using a printf, or do whatever you want to do with it, and then traverse the right. So node left right, if your tree is null, you're done. But here we want to print the root data first, and then we want to traverse the left, and then we want to traverse the right. And left right node, if the tree is null, don't do anything otherwise traverse the left, traverse the right, and then print the root data. So it's really the same 4 lines of code. The only difference is where this print happens, in the middle, in the beginning, or at the end. And if you're going to copy and paste, don't go to make sure you are calling NLR recursively inside NLR. Make sure you're calling LRN recursively inside LRN. Right? I sometimes get assignments where somebody wrote this first, and then copied it, renamed it, moved print, but didn't change these LNRs to NLRs and didn't change them to LRNs, and then your traverse orders are wrong. So copy paste is good, but make sure that what you've written makes sense. Not even different to my understanding, literally all the same code, just rearranged, I believe. That's what I thought. So in our LNR, should we print out space between the comma and the last name? The example in the assignment sheet has that, but the sample executable doesn't have a space. Yay for happy noises. Let me see what the assignment says. Because I know you asked me about this yesterday, but I didn't see in the assignment where I said anything about commas and spaces. Let's see. Print out space between a comma and the last name. So this is for the traversal, right? So line traversal, comma, space, and then the name. But the sample executable doesn't have a space there. Well, that's an unfortunate inconsistency. Alright, well I am not going to be picky about that then. But yeah, I'm showing a space here, I'm not showing it here. So if you want to be able to use the difference command to know whether or not your output's exactly matching mine, then I would say do not print a space there. But yeah, I do seem to show a space in here. So I won't take off for that if you put a space in, but it's probably easiest if you don't. The main thing that's critical here, though, is the order. I want to see first name followed by last name with a comma in between. Alright, I think we made it to the end of my chat window. Unless I missed something. Yeah, that's last comma first. Yeah, last name, comma, first name. Diff just takes two file names, tells you if they're different or not. So, so I can take this command and put it into F1, and I'll just type in a dump command and a ctrl-D. And let's say that my output missed one name and had a strange license plate down here, right? So here's what the test program gave me. Here's what my program gave me. How do I know if they're the same or not, right? So just difference F1, F2, and it'll show you the exact differences. And this is telling you that F1 had an extra line in there that F2 did not, and this is telling you that F1 had this and F2 had that. So if your files are exactly the same, then diff doesn't give you any differences. So that's just a nice way if you're trying to really nail down output, or look for some condition in a file, right, that it will go through and compare these files, and does a good job, right? It doesn't get tripped up because, you know, I can have a bunch of lines here that are missing, and I could have, you know, a bunch of lines here that are new. And technically, if I just compare byte for byte or line for line, every line in F1 is different from every line in F2, right? But it's smart enough that it will just look for, you know, sections that are different. And so this is saying, you know, this stuff was an F1 but not F2, this was an F2 but not F1. So it's a nice function. Let's see, every function is supposed to be recursive, right? A lot of them are. LNR, LRN, delete, search, add. Definitely not your main program, but yeah, I think probably all the functions you're required to implement are going to be recursive. Let's see what we got. Height is recursive, balanced, add, search, delete, tree free, yeah. That's a good observation. Yeah, let me run through freeing memory, and then let's run through deletion. My paper feels really dark to me for some reason. Alright. Alright, how do we free a tree called T? There's a poem starting there. How do we free a tree called T? if your tree is empty, there's nothing to do. Right? If you call free tree with a null argument, then you have a tree containing no nodes. There's nothing to do, just exit. Otherwise, let's free the left subtree. Let's free the right subtree. And then let's free the root node. So yeah, basically reusing your print algorithm. Although here I'm doing something more like left-right node. You can use temporary variables to keep track of things, but I don't really want to free the root node until I'm done using it to refer to the left and the right. So if I'm doing the shortened version here, right, if the root's null, nothing to do. Free the left subtree, free the right subtree, and then free the node associated with the root. And you notice I haven't actually called the free function yet. That's going to happen inside free node. So how do we free a node? Well, node's never going to be null. I'm not going to call this with a null, because if t is null, I would have exited my free tree function early. So I don't really need to worry about n being null. Here's what I want to do. I want to free the memory I allocated for the plate and the last name and the first name, and then I can free the node n itself. Alright, so that's you know, nice recursive traversal of your tree. And just make sure that instead of just saying, you know, free t, we actually free the fields associated with it. And you know, I could do this over here if I wanted, just modularizing. Alright, does that make sense? So technically this will free the leaf nodes first. You are right. And you kind of have to do that if you're not using a lot of temporary variables. Once you free a node, its children should already have been freed, according to this. So the leaves get pruned first. This is how you would cut down a tree if you wanted to do such a thing, right? You'd cut down the leaves first, and you'd work your way towards the root. And by the time you get to the root, there's no branches or leaves hanging off of it, and so it's a single call, right? That's a morbid example, because you shouldn't cut down trees. And yeah, this is one of these things about recursion. It's fun to think about, you know, where stuff actually happens, and a lot of stuff we sort of think of it from, you know, the root on down, but the actual action happens at the leaf nodes first. Same with the height function. When we try to calculate the height of a tree, the first thing we do is we calculate the height of, you know, all of the leaf nodes, and then we move up one level and calculate the height of the subtrees, of which those are children, and so on and so forth. Would I get points off if I freed from the top down with an exponential number of temp variables? Are you really doing that, or is this a rhetorical question? Exponential number of temp variables, if you malloc those, you could get away with an exponential number, but then you'd have to free that space. If those are hardwired, like an array of temporaries, then you're limiting the size of your algorithm's workspace. So I think you'd have to allocate more stuff for that, and then you'd have to free those. But one could do it, right? One could make a free algorithm that's not recursive at all, but, you know, does a tree traversal using a stack. Or you could do this with a queue. You could do a breadth first traversal and, you know, free on your way down. There's lots of ways to do it. A lot of our goal in the algorithms that we're going over is to not have to think too much, right? Once we understand it. It takes a lot of thinking to understand it. But this is, you know, once you've done this and you've seen this and you understand it, this is pretty easy to write and maintain and understand and modify. So, but definitely not the only way to do this kind of thing. Alright, so someone asked about deletion. So let's go over that. And I'll continue to work with a tree of integers. There's a nice fluffy tree. And if we want to delete a number, let's say we want to delete the number 80. So our recursive part of our delete function is going to kick in, right? So what's our main delete algorithm? So delete tree comma number. So if our number is smaller than the root node, then we want to delete from the left subtree. So delete from the left subtree, take the return value from that, make that the left child of t, and return t. If our number is bigger than the root node, then change the right subtree to be the result of deleting your number from the right subtree, and return the root. Otherwise, we got to delete the root. So let's look at the recursion. Suppose we want to delete an 80. Okay, so we're trying to remove this node right here. So we're going to compare 80 to the root node. 80 is bigger than 25, so what do we want to do? Delete from this tree an 80. And when we're done, we're going to replace the right child with whatever this tree looks like with 80 removed. Okay, how do we delete 80 from here? Compare 80 to the root. It's bigger, so we're going to delete the 80 from this right subtree, and whatever the resulting tree is, we're going to make 40's right child equal to that. So now we've gone down 2 levels of recursion, and we've made a call to delete, which says delete 80 from this tree. And we'll compare 80 to the root data. It's not bigger, it's not less than, it's equal. So now we're in the workhorse of the code where we need to delete the root. Okay, how do we delete the root of this tree? Find the largest node in the left subtree, make that the new root. And there's details for that, but let's work our way down. So what's the left subtree? It's all of this stuff starting with 60. What's the largest node in there? It's a 67. So we're going to change 67 to be the root. And then the parent of 67 is going to adopt 66's left child on its right. So this is going to pick up 66. And then that delete function, right, this part of the code down here, is going to return the new root. Which means that in our recursive call, we're going to set t right, back when t was equal to the 40, we're going to set t right equal to this new tree. Right, because before we do this, 40 is still pointing to an 80. But when we come back from this recursion, 40's right child will be set up to point to 67. And then when we come back from the recursion on the original node, 25's right child will be set to 40, which is what it already was, and will return the original root. So this is the tree we get back with 67 delete, with 80 deleted. And it's all pointer manipulation. We're not moving data around. We don't actually take the name and the first name and the last name and the plate and copy them from here to here. We don't move the data. We change pointers. We're going to change 65's right pointer to be whatever 67's left pointer was. And we're going to change 67's left pointer to match 80's left and 67's right to match 80's right. And then we're going to change 40's right child to be wherever 67 is. And that makes your picture look like this. Alright, and then the complicating details, which is this business of once you've decided you're going to delete the root of a tree, how do you find the largest thing in the left subtree? Well, move down one spot to the left so that this is the left subtree, and now starting from the root of this, just go as far right as possible. So 60, 65, 67, that's as far right as I can go. That's the largest node. That's what's going to become the new root of this tree. There's a minor edge case, which is if my left subtree looked like this, and I want to find the largest node in this left subtree. Well, I start from the root, but I cannot move to the right. The root doesn't have anything on the right, in which case the root is the largest node. And so this would be my largest node in the subtree, and that would basically become the new root of this tree. The more extreme edge case is I want to delete 80 from a tree, and there's nothing to the left of 80. So the algorithm says find the largest node in the left subtree, but the left subtree is null. It has no nodes. And that's the real edge case. And in that case, and that case only, we use a different algorithm. And the algorithm for deleting the root of a tree with nothing on the left is just take its right child, that's the new root. So we would just return this node's right child after freeing this node. And then the code that called us recursively, in this case deleting 80 from this tree rooted at 40, would say 40 right equals, and it'll set it equal to 100. Those are the bulk of the edge cases. The only real edge case, the strongest edge case is if you're deleting the root of a tree that has nothing on the left. And in that case, just move the root down to the root's right child. And that takes care of the case where you're deleting from, say, a tree that only has one node, while the root node's equal to the thing I'm trying to delete. If there's a left subtree, we'll replace the root with the thing that's largest in the left, but there isn't, so the algorithm is make the root whatever the root's right child is, while the right child's root is null, so this is going to return the new root as null. And your tree goes from having one node to having no nodes. So some of these edge cases actually don't have to be handled as edge cases. They work out correctly in the code. All right, good. Other questions? So we've gone over file I/O. We know how to duplicate the plate information using malloc and string copy. We know about adding 1 to the string length, traversing the tree, doing the tree manipulations. We know how to free memory at the end, how to print the stuff. We went over balance yesterday, or height yesterday. Everybody clear on the balance algorithm to tell whether or not the tree is balanced? Alright, make sure you do all three things. Make sure that the left and right subtrees have similar heights. Make sure the left tree is balanced. Make sure the right tree is balanced. Okay, so is this tree balanced or not? I don't know. But here's how we can find out. Look at the left and right subtrees. find their heights. Okay, this has a height of 2. This has a height of 4. Their heights are not close. So the tree's not balanced. We're done right there. Now, if my tree looked like this, I would calculate the height of the left subtree, that's 3, the height of the right subtree, 1, 2, 3, 4. The heights are within 1, so it could be balanced, but we're not ready to say yet that it's balanced or not. We've passed the first of 3 criteria. The heights are close, they're within 1 of each other. The next question is this tree itself balanced? And then the last question is this tree itself balanced? And if both of those are balanced, then we can say the tree is balanced. So how do we know if this is balanced? Well, let's look at the left and right subtrees. So here's the left subtree. Here's the right subtree. Left subtree, the height equals 2. Right subtree, the height equals -1. Those are not close to each other. They differ by 3. So this is not balanced, therefore the original tree is not balanced. And you can think about kind of the pathologies that this is picking up. So one is this case where the left and right subtrees have exactly the same height, but this is definitely not balanced. So the height alone is not enough to tell us that the tree is balanced. Right, the other pathology is this. So if I look at the subtrees, here's the left subtree, here's the right subtree. While the left subtree is beautifully balanced, that's like the most balanced tree in the world. And the right subtree is also beautifully balanced. But the whole tree is not. Why? Because the heights of the left and right subtrees differ significantly. This has a height of 3, this has a height of 0. So you got to make sure left and right subtrees are balanced and also that the heights are close to each other. And so just code that up using the balance function and the height function. Right? So find the height of tree left, tree right. Subtract them if it's less than or equal to 1, bigger than or equal to -1. Continue, see if the left and right subtrees are balanced. If all 3 are true, the tree is balanced. If any of those fail, the tree is not balanced. And what's our edge case? What can we do to stop us from calling balance forever and ever? Didn't know there was going to be a question, did you? Check to see if the root is null. Perfect. Our edge case is if we ask for a null tree, then we just say, yes, the tree is balanced. By definition, a tree with no nodes in it is considered balanced. If you change that, then nothing is going to be balanced. All right, good. I think that's everything for PA4. And the people who have come in and shown me their code, looks like you're in good shape. There's, as I warned you up front, there's a lot of pieces to this, and there's a lot of details to work out. But if you're working through it methodically, hopefully you're building up the behavior, and it's, you know, not going to be any big surprise at the end, like, oh, none of my code compiles, or, you know, I segfault every time I read the database or something, right? Keep building it up, adding more behavior, And checkpoint your code, right? My suggestion, put it in Git, push it over, right? So that if, you know, something happens, you decide, I'm going to write my delete function tonight, but I'm going to do it with my eyes closed, right? And you start hacking up your code to add delete, and your whole code just like breaks, right? You've got ways to go back to older versions of it, right? So keep backups and checkpointing, and submit stuff along the way. And I would prefer this didn't happen, but you know, if something really bad happens and you can say, hey, I broke my code, is there any way you can look at the version that I had on Thursday instead of Friday, right? I'll work with you to go back and look at that old version. That's an emergency measure. I don't want you to say, like, can you grade whichever version of my code worked best or something like that. But you know, it's good to have checkpoints along the way in case something breaks. And then you can code fearlessly, right? You can start modifying huge swaths of code to try to make delete work, and so on. Yeah, not an option this week. All right, let's see. So we have some more sorts to talk about. I was going to talk about merge sort today. We have about 3.5 minutes. Let me give you the high level vision of a merge sort. Why does delete turn a different color in C? I don't know. I don't think it's a built-in. I don't usually have color turned on for my editors. So it could be a keyword, or maybe it recognizes it as a function or something like that. Yeah, I go monochrome. Actually, I'm bichrome because I do like green and black. So I mentioned when I sort papers, right? I'm alphabetizing them so I can enter grades. I tend to do an insertion sort. So I take the first paper, I put it in my pile. I take the next paper, put it in my pile. So my output pile is always alphabetized. Insertion sort is order n squared. And in a class where I have 60 students, how much work am I doing to alphabetize that? Well, on the order of 1,800 operations, right? N squared over 2. 10 students in class, it's not a big deal. It's like 50 operations. 60 students in class, it's almost 2,000 comparisons of one name to another to alphabetize. So somewhere, you know, as my class sizes grew, I started to realize I was spending a lot of time just alphabetizing papers so that I could enter grades in Canvas. And so what I actually seem to do is I use an insertion sort for small chunks for maybe like 10 or 15 papers. But I end up with multiple piles, each of which are sorted but need to be put together. And this is the idea of a merge sort. So a merge sort works like this. You take your list and you split it roughly in half. Okay, I had an even number of things here, so I could split that exactly in half. And then, somehow, using something we call magic, we sort each of these lists. Alright, so there's some magic step that takes here. So this is our merge sort algorithm. So split your list in half. Use some magic to sort each of those halves. And then interleave them, mix them together in a way that preserves the sort. And interleaving two sorted piles is really easy. I look at the first thing in each pile and I pick the smallest. One is smaller, so I'm going to put that right here. I look at the first thing in each pile, 2 or 3. 2 is smaller, so 2 goes here. Look at the first thing in each pile, 4 or 3. 3 is smaller, so 3 goes here. Look at the 4 and the 5. 4 goes here. Look at the 6 and the 5. 5 goes here. Look at the 6 and the 7. 6 goes here. Look at the 8 and the 7. 7 goes there. Look at the 8 and the 10. That's an 8. And now I've got nothing left in this pile, so I just take these remaining entries and I just copy them to the output. So that's a merge sort. And the only trick is, what is this magic step? How do we sort each of these sublists? Interleaving is pretty easy to write. Splitting an array in half is pretty easy to do in theory. But what's our magic step going to be? How are we going to sort these sublists? So think about that, and we'll start with that tomorrow. See if you can come up with a solution for that magic step 2. All right, have a good one. I will see you next time.